What specific problem does the new method or algorithm aim to solve?
The new method or algorithm aims to solve the problem of representational convergence in neural network models. It explores the growing similarity in how data points are represented in different neural network models, spanning across various model architectures, training objectives, and data modalities. The central hypothesis is that different models are converging towards a representation of reality, specifically, a statistical model of the underlying reality that generates the observed data. The method aims to understand why this convergence is happening, whether it will continue, and where it ultimately leads to. It investigates how models align with each other, across modalities, and even with biological representations in the brain. The goal is to uncover the principles driving this convergence, and to determine the nature of the endpoint representation that models are converging towards.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method works by exploring representational convergence in AI systems. It argues that different neural network models are converging towards a shared representation of reality, referred to as the Platonic representation. This convergence is driven by models aiming to capture the joint distribution over events in the world that generate observed data. The method involves using contrastive learners that model observations co-occurring together and learn representations that approximate the log odds ratio through a dot product kernel. By optimizing these representations, the method converges to a point where the kernel represents certain pairwise statistics of the underlying reality. This convergence is observed not only within the same modality, but also across different modalities, such as vision and language. The method also considers the role of scaling model capacity, simplicity bias, and task generality in facilitating representational convergence. Additionally, it discusses the implications of alignment in improving downstream task performance, the potential reduction of hallucination and bias with scale, and the adaptability of models to different modalities. The method acknowledges limitations in convergence across all domains and the influence of sociological bias and special-purpose intelligences on the convergence of representations. Overall, the method provides a framework for understanding how AI systems are converging towards a unified and proficient representation of reality across various domains and modalities.
What are the theoretical or practical benefits of using this method?
The theoretical benefits of using the method described in the paper include the convergence of representations across different neural network models, leading to a unified representation of reality. This convergence is driven by the increasing scale of models and the alignment towards a statistical model of the underlying reality. The method also suggests that as models scale up, they converge towards a smaller solution set with reduced epistemic uncertainty. Additionally, the method highlights the importance of multitask objectives in optimizing representations and the role of simplicity bias in driving convergence towards simpler solutions. Practically, the method allows for improved downstream performance on tasks such as common sense reasoning and mathematical problem solving as alignment increases. It also enables the sharing of training data across modalities, leading to more efficient learning and adaptation across different domains. The method can potentially reduce hallucinations and biases in large models by aligning representations more accurately with the data. Furthermore, it facilitates ease of translation and adaptation across modalities, making it simpler to find mappings between different domains even without paired data. Overall, the method offers a path towards understanding and utilizing representations that are proficient across various domains and modalities, grounded in the statistical properties of the underlying world.
How is the method validated or tested?
The method is validated or tested through various experiments and analyses outlined in the paper. One validation method used is model stitching, where two models are integrated via a learn-defined stitching layer to create a new stitched model. If the new model performs well, it indicates that the original models have compatible representations at certain layers. Another validation method is through measuring representational alignment using a mutual nearest neighbor metric, which calculates the mean intersection of the nearest neighbor sets induced by two kernels normalized by a constant. This metric helps assess the similarity between representations induced by different models. Additionally, experiments were conducted on CIFAR-10 classification, where it was found that larger models exhibit greater alignment with each other compared to smaller ones, indicating that alignment increases with model scale. Furthermore, the paper discusses a case study on color distances in learned language representations and how they mirror human perception, demonstrating convergence on real data. These experiments and analyses provide empirical evidence supporting the hypothesis of representations converging towards a unified model proficient across various domains and modalities.
What results were achieved with this new method?
The paper discusses the concept of representational convergence in AI systems, where different neural network models align towards a unified representation of reality. The results achieved with this new method include the observation that different neural networks, even with different architectures and objectives, can have aligned representations. The paper presents evidence from studies where vision models trained on different datasets align well, and models trained using self-supervised objectives align closely with supervised counterparts. Additionally, the paper discusses how alignment increases with model scale, showing that larger models exhibit greater alignment with each other. The study also explores convergence across modalities, indicating that models trained on different data modalities do converge. The paper provides evidence that scaling is sufficient for convergence, but not necessarily efficient, and that training data can be shared across modalities to improve representations. Furthermore, the paper suggests that scaling may reduce hallucination and bias in models, and that different modalities may contain different information, impacting the level of convergence. Overall, the results demonstrate that AI models are indeed converging towards a more accurate representation of reality, leading to improved performance on downstream tasks and facilitating ease of translation and adaptation across modalities.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method outlined in the paper include the fact that the convergence towards a unified representation is mainly focused on vision and language modalities, with other domains like robotics not showing the same level of convergence yet. This discrepancy is attributed to limitations in robotics hardware, which affects the quantity and diversity of training data available. Additionally, there is a concern about sociological bias in AI model development, where the goal of mimicking human reasoning could lead to convergence towards human-like representations, potentially limiting the exploration of other forms of intelligence. Furthermore, the method may not apply to special-purpose intelligences optimized for specific tasks, as these systems may have effective representations that are detached from the unified reality model. The paper also acknowledges the need for further research to explain the level of alignment achieved by different models, as the mutual nearest neighbor metric used in the experiments only reached a score of 0.16 out of a theoretical maximum of 1, leaving room for interpretation regarding the strength of alignment and potential remaining differences.